this week we're going to be reviewing some basics of calculus. We're going to be focusing on derivatives. So this may be review, and probably is review for a lot of you. Alright, so let's start off by talking about what a derivative is. So let's think about this graphically. Alright, and I apologize, my graph does not look that great. I'm still getting used to this tablet. Alright, so let's say I have some function f of x. Alright, so the derivative is basically just the slope of the line at any given point. So if you draw the tangent line, the slope of that line is the derivative of the function f of x. So we want to write the derivative of f with respect to x. We just write df dx. That's the instantaneous slope of the line. Let's make this a little bit more concrete by talking about velocity and acceleration. Alright, so velocity is the derivative of position with respect to time. And acceleration is the derivative of velocity with respect to time. So here we're thinking about the derivative as the rate of change of a quantity. So velocity is the rate of change of position, acceleration is the rate of change of velocity. So if you've been teaching physics algebra based for a while and haven't been doing it with calculus very often, then you may notice that a lot of what I write as derivatives is written as, say, division in the algebra-based physics class. So you might be writing something like velocity equals the change in position divided by the change in time. Or you might be writing that acceleration is the change in velocity divided by the change in time. And that'll get you average velocity and average acceleration. But basically, these quantities can be generalized as derivatives. Alright, let's look at some more graphs. So let's say we have a plot of position as a function of time. Alright, so let's say the position's increasing approximately quadratically. Alright, so let's look at how the slope changes. Alright, so over here, the slope is small and then it gets steeper, so the slope is increasing. Again, I apologize for the quality of my drawings. Alright, so velocity is the slope of this line, so how is that going to change? Alright, so here we see, okay, velocity is the slope of position. So here the slope is small, here the slope is bigger, so it's increasing. And let's say it's increasing approximately linearly. So we can say our velocity is just increasing as a straight line. Now acceleration is the slope of velocity. So what does our acceleration look like in this case? Alright, so the slope of velocity is just a straight line, so the slope of velocity as a function of time is not increasing. So acceleration, the derivative, is just a constant. And it's a positive slope, so we just have some line above zero. So I actually teach this sort of concept graphically to my students who are just taking conceptual physics and they're not learning calculus. I have them doing this. So they're doing calculus, but I don't tell them they're doing calculus. Let's take a moment and you can try a few things yourself. So for this first question, what I want you to do is I'm going to give you the x versus t graph. I want you to sketch the velocity versus time graph. Alright, so let me draw you this position versus time graph. Alright, so given this position versus time graph, sketch your velocity versus time graph. Alright, and for the second question I want you to do is I'm going to give you the velocity versus time graph. I want you to sketch the acceleration versus time graph. So here's your velocity versus time axis. Alright, let's say your velocity looks like this. Alright, so at this point, you should pause the video, work these out for yourself, and then when you're done trying it out, you can go ahead and push play again. And if you want to discuss it, go ahead and go over to the problem solving discussion forum and write any of your thoughts about this question. Alright, so here's the answer. Alright, so we're going to draw the velocity versus time graph. Alright, so for the first time period, the position is increasing linearly at a constant rate. So the slope of the line is constant and it's positive. Oops. So for the first time period, it's just going to be a horizontal line. Alright, after that, the position versus time graph stops changing. It's just a horizontal line. So position isn't changing anymore, which means that the velocity goes to 0. Alright, for the second question, we're drawing the acceleration versus time graph. Alright, so how's this working? Well, actually, we're going to need the negative. Alright, so velocity is decreasing at a constant rate. So we need a constant horizontal negative value, because this is linear, so it's a constant acceleration, but it's negative because velocity is decreasing. Alright, if you have any questions about this solution, please go post them in the problem solving forum or come talk to me in office hours. Alright, so let's look at some common derivatives. Now, instead of doing it graphically, we're going to look at the equations. Alright, so let's say you just have a constant. And we'll represent a constant just with a capital C. And we want to know the derivative of that constant. So you know, it could just be the number 5. F of x equals 5. Alright, well, a constant isn't changing, so what is rate of change? 0. The derivative of any constant is 0. Alright, now, the most common rule you need to know is the power rule. Alright, so in general form, we say the derivative of x to any power, x to the n, is that you bring down the n in front, and then you knock down the power of the exponent. Alright, and these formulas are nice in general, but I often find that the first time I see them, they don't really make a lot of sense, so I prefer to show examples. Alright, so let's say we're looking at the derivative of x to the 4th power. Alright, so we're just going to bring down the 4, and then we're going to knock the 4 in the exponent down to a 3. 4x cubed. Done. So this is a very common rule that you should know. Let's say that there's a constant in front. What do you do then? Alright, well, all you have to do is multiply. Let's do an example. So I really don't find that the general formulas are very helpful for me for the way that I think, but everyone thinks a little bit differently. Alright, so let's say now that our derivative, we're taking the derivative of the function 4x squared. Alright, so we just leave that 4 out in front, bring down your 2, you're going to multiply that 2 times the 4, and then you knock down the power of 2 to, 1, which obviously you don't have to write an exponent, so this is 8x. That's your derivative. Done. Alright, so it's a very common rule, you'll need to use it all the time. Hopefully it looks familiar to most of you. Alright, you also need to be ready to deal with a lot of trig functions. So at the very least, you need to know how to find the derivative of cosine and sine. And these, well, a lot of my students get mixed up about signs. Which one gets a negative sign? They need to think about it. It's a pretty common thing to get mixed up about it. Alright, so let's say you're taking the derivative of cosine. The derivative of cosine is minus sine. And the derivative of sine is cosine. So generally, my students can remember that cosine goes to sine and that sine goes to cosine, but they'll forget which one the negative sign should be on. So just make sure you're careful when you're doing derivatives with trig functions. Alright, now the easiest derivative to do is the exponential, actually. Alright, so what you do is we're taking the derivative of e to the x. Well, it turns out the derivative of e to the x is just e to the x. You don't have to change anything, so it's really easy to remember. Alright, and the inverse of exponential, if you're doing logarithms, the derivative of log x is 1 over x. Alright, so those are all the ones I expect you to remember. You can find out a lot more just by using an integral table. The recommended book I have listed in the syllabus has integral tables in it, and you're welcome to use it on your exams. I don't expect you to have to memorize everything, but these ones are so common that it really is best to memorize these. But you'll memorize them just by the process of using them all the time. Alright, and just one more simple rule. If you're adding functions together, and I'm betting you can figure this out. So if you have the derivative, say, of two functions that are added together, you just add their derivatives together. So let's say we're taking the derivative of cosine x plus x squared. Alright, the derivative of that is just the derivative of cosine, so that's minus sine x, plus the derivative of x squared, which is 2x. Alright, done. Simple enough. Alright, so I want you now to just try out some basic ones yourself, just for practice. If you've taken calculus recently, this will be really easy for you. Alright, so let's just say I'm going to give you 3 functions to take the derivative of. Just try them out. Alright, so at this point you should pause the video, work out these examples, and if you need to talk about it, again, go over to the problem solving discussion on eCollege. Alright, so what are our answers? Alright, the first one is all power rule. Alright, we bring down the 5, multiply it times the 2, we get 10. We knock down the power of the exponent to 4. Next one, bring down the 2, multiply it times 7, we have 14. Knock down the power from 2 to 1, so we have 14x. And the last one is just a constant, so it's 0. And you don't have to write the 0. Alright, so the derivative for the second one. Alright, we start out, the derivative of an exponential is the exponential. Alright, the derivative of cosine is minus sine. So we have e to the x plus sine x. Alright, and this is where you have to watch out for sign errors. They're really easy to make. Alright, and then the last one, alright, we have 3, and the derivative of log x is 1 over x, so we'll just put this 3 over x. And then the derivative of x squared, we just bring down the 2, knock down the power, 2x. Alright. Not too bad, I hope. Alright, so these are a bunch of rules that we're applying that you can memorize, but I want to make sure that they make conceptual sense to you. So now what I want you to do is graph a couple of functions and graph their derivatives and make sure that they make sense. Alright, so what I want you to do, alright, I'm going to give you 3 functions. I want you to graph the function, then I want you to find the derivative and graph the derivative. And I want you to make sure that how it looks graphically makes sense with how you conceptually understand derivatives. Alright, so pause the video and try these out. Okay, let's sketch the functions. Alright, so let's sketch x squared. Alright, x squared is just a parabola. And when you're doing this, don't stress about getting the exact points at the right places. We're just sketching to get a feel for how the function changes. And again, I apologize for the poor quality of my drawings. That happens when I draw on whiteboards and chalkboards too. Things just look better on my little notebook paper than they do in my presentations, unfortunately. Alright, so what's the derivative of this f of x? Alright, we've already done this actually, so it's 2x. Alright, what's that look like? This looks like a line that passes through the origin. Yes, I made it through the origin. Okay, so what are we doing here? So let's look at the rate of change of this function. I will try to draw tangent lines. Okay. One of these days I'll get good at drawing graphs on a tablet. Alright, so at less than 0, the slope of x squared is negative. It starts out steep, so it's a large negative value. And then it becomes more gentle slope, so the slope is decreasing. Well, the magnitude is decreasing. So we start out with a large negative value and it's decreasing, and when we hit the origin right here, see where x equals 0, the slope is 0. Alright, that makes sense. Alright, then we have a gentle slope again, a small slope, and then it's increasing. Alright, it's getting bigger. Alright, makes sense. Let's look at sine. Alright, so sine starts out at 0, it increases, comes down, and comes back up. Alright, what's the derivative of sine? That's cosine. Alright, cosine. Well, cosine 0 is over here actually. At x equals 0, cosine is 1. Alright. I always find it a little bit challenging to draw cosine. Alright, let's think about this. Alright, so sine has a pretty steep slope at x equals 0. Alright, and cosine is positive there. That makes sense. Alright, then sine has a slope of 0 up here at this peak. Alright, so that's right here where cosine passes through 0. Alright, then over here, sine is actually pretty linear right here. So that's a negative slope. Alright, so that passes through right here. Alright, and then we have down here where sine has, and that's where sine is at 0 slope. That's where cosine comes through here. Alright, so that makes sense. Alright, let's look at our exponential. So remember about the exponential is that it's its own derivative. Alright, e to the 0 is 1, so it's going to pass through right at this point right here if this is 1. And it slopes up pretty quickly. It's its own derivative. Well, this one's an interesting one to look at. Here. Let's see if this helps. Alright. So the exponential is its own derivative. So let's look at this. So over here, the slope is small. Alright, over here is small. It's getting steeper. Alright, it's increasing. It's getting steeper. It's increasing. Yeah, so that one does work out. And remember, if any of this is confusing, please go to the discussion forum or come talk to me in office hours or make an appointment with me. I'm happy to talk about any of this with you. Alright, let's go back to the equations and the formulas and look at a little bit more complicated derivatives. So let's say we're doing the chain rule. Now the chain rule, I find if you write in the general form before you've ever tried it, makes no sense whatsoever. So I think it's really important to start with examples when talking about the chain rule. Now everyone thinks a little bit differently, so you might disagree with me, but this is what I find works the best. Alright, so let's say we're taking the derivative of cosine 2x. Alright, and it's perfectly valid to write it this way, but I found that when my students last year were learning about derivatives that they would get confused if I didn't draw parentheses everywhere. So just remember, the cosine is of the function 2x. We're taking the derivative of the whole thing. So you don't have to write these parentheses, but just because we're starting out with the review, I'm going to draw excess parentheses. So how do we do this? Alright, so the chain rule is basically when you have a function inside a function. Here, 2x is our inside function, and cosine is our big function. So we take the derivative of the big function. So the derivative of cosine is negative sine. And we leave the insides alone. So we keep that 2x. And then we're going to multiply that times the derivative of the inside function. So the derivative of 2x is 2. So we're multiplying by 2. Alright, so the derivative is minus 2 times the sine of 2x. Alright, so you may find you're comfortable writing it this way. Another way to write it, we can use another notation that makes the steps we're doing more clear. So you just pick the way that makes the most sense to you. Alright, so this is the derivative we want to take. d dx cosine 2x. So we're going to write this using u notation. So we write our inner function as u. The inner function u equals 2x. We need to know the derivative of the inner function. Alright, that's 2. Alright, so what we want to do is we take the derivative of the big function, but now instead of writing cosine of 2x, we're just writing cosine of u, remember, because we've said that u equals 2x. And now we're taking the derivative as a function of u. Alright, and then we take that and multiply it times the derivative du dx. Alright, so the derivative of cosine of u with respect to u is minus sine u. And then we want to multiply that times du dx, which we already found is 2. So we get minus 2 sine u. And at this point, you have to remember to plug u back in. So we get minus 2 sine 2x. Alright, so these are two different ways of finding the same derivative. And this is the rule that my students usually find the most confusing, and I wish I could see your faces right now so you could tell me if this made sense or not. So please, let me know in the forum or message me. Just let me know if this makes sense. Alright, so now we can write the general abstract form. So we would write that as, we have a function that has an inner function. A function of u that's a function of x. The derivative of this function as a function of x equals the derivative of the outer function as a function of the inner function times the derivative of the inner function with respect to x. Alright. This is the most confusing one. Please let me know if this didn't make sense, and I'll be happy to try to explain it to you again. And you know, I love talking to students one-on-one, and I can really make sure you're getting the help that you need. So please don't hesitate to contact me if you ever want to talk to me. And if you're looking in your integral table, you may recognize this sort of notation with the u's everywhere. Like I have an integral table that says stuff like this. d dx cosine u equals minus sine u du dx. And it would be great if you would comment in the forum if you understand how to use your integral tables or not, and your derivative tables in your book. We'll go over that more next week, but I would just like to know how much you need me to go over it. Okay. Now I'm going to give you a few chain rule examples to try yourself. And again, I'm writing way more parentheses than I have to, and if you're comfortable with this sort of thing, you probably see my parentheses as completely unnecessary, but it's really helpful for a lot of people when they're first learning calculus to use too many parentheses. Alright, and this one, the notation may also be unfamiliar to you, depends how long it's been since you've dealt with trig. This means that cosine is cubed. So another way of writing this is that the function cosine of x is cubed. Alright, so go ahead and try those out, go discuss them in the forum, pause the video, and then press play when you're ready to go again. Alright, so for this first one, this is e to the 4x. So u equals 4x. That's your inner function. Alright, what's the derivative of the inner function? That's just 4. Alright, so what we have is we take the derivative of the big function. Exponential's derivative is just itself, so that stays e to the 4x. And then we multiply by du dx, so we multiply times 4, so we get 4e to the 4x. Alright, this next one, our inner function is x squared. Alright, what's the derivative of our inner function? 2x. Alright, so we take the derivative of the outer function, so the derivative of sine is cosine. Then we multiply times the derivative of the inner function. So that equals 2x cosine x squared. Alright, this one, so when you write it this way, it's a little bit less obvious. When you write it this way, it becomes more obvious what the inner function is. So the inner function is cosine. So we take the derivative of the inner function, and that's minus sine x. So really, we could rewrite this. So we're finding the derivative of the outer function. So the outer function is u cubed. And we're multiplying that times the derivative of the inner function. Alright, so this is 3u squared times du dx. So let's plug in what all those things are. U is cosine, so this is 3 cosine squared x times minus sine x. So the answer is minus 3 cosine squared x sine x. Alright, I hope that makes sense. This is really the most confusing part of derivatives. Aside from how hard they are to say, apparently, the hardest part of them is doing the chain rule. Nothing else is too bad about them. Alright, let's move on. Now we're going to talk about the product rule. Okay, this is when you have two functions multiply together. So this one, I think it's easier to write the general formula and then do an example. Your opinion may differ. Hopefully, I make sense to you. Alright, so say we're taking the derivative of two functions multiplied together. So we're going to call those functions f of x and g of x. Alright, so the derivative then is you leave the second function alone, and then you multiply it times the derivative of the first function, and then you add that to leaving the first function alone and multiplying that times the derivative of the second function. Okay, right, this sounds pretty abstract. Let's look at an example. Okay, so we have our function is x cubed times cosine x. All right, let's do this. So first we're going to leave, let's see, well, it doesn't matter what order you do it in. You know, you can flip these two terms. You know, addition doesn't care what order you do it in. All right, so first we're going to take the derivative of d, I'm going to go d dx. We're going to take the derivative of x cubed, but we're going to leave cosine alone. And then on the next term, we're going to leave x cubed alone, and we're going to write the derivative of cosine x. Okay. So, right, you could flip the order you write these in. You could flip the order you write these in. Order doesn't matter when you're just multiplying and adding. But you know that. Okay, so the derivative of x cubed, bring down the 3, knock down the power, and then just multiply times cosine x. All right, this one, we've got our x cubed left alone. The derivative of cosine is minus sine. All right, just simplify it slightly. And you'll get to the point where you don't have to write things out step by step this way after you do this enough times. And if this is all review for you, then that's probably true for you, that you don't have to write down every single one of these steps either. Alright, so let's go ahead and give you some examples to try out. Alright, so the first one is of the exponential times sine. The second one is log times cosine. Oh, and I should specify, I mean natural log every time I say log. Alright, and the third one is x squared times log of x. Let's go ahead, take all of these derivatives using the product rule. Remember, pause the video and hit play again when you're ready to see how your work checked out. Alright, so this first one. First, what we're going to do is we're going to take the derivative of e to the x and just multiply that times sine x. And then for the second term, we're going to leave e to the x alone and take the derivative of sine x. So we have e to the x sine x plus e to the x cosine x. And if you like, not required, but if you like, you can simplify and write e to the x sine x plus cosine x. I find it difficult to resist rewriting it this way, but everyone has their own personal preferences. Alright, so this next one, we're going to take the derivative of log, then we're going to multiply that times cosine x. Then we're going to leave log alone and take the derivative of cosine. So we get cosine of x divided by x minus log x times sine x. So I'm kind of skipping a few steps here. Let me know if it bothers you if I do that, and I will cut back on doing that next time. Alright, so the last one, first we'll take the derivative of x squared, multiply that times log x, then add that to x squared left alone times the derivative of log x. Alright, so the derivative of x squared is 2x, so we have 2x times log x. Then we have x squared times the derivative of log x, which is 1 over x. Now this one I definitely want to simplify, so I get 2x log x. You see this one I can cross off here, and then I just have plus x. Alright, now this one you can also simplify, say if you like to pull out the x, then you can say 2 log x plus 1. Alright, well, let me know if you have any questions. This is where we are going to stop for today. Next week we may do a little bit more on derivatives, but we're mostly going to focus on integration next week. Let me know how much of this was review for you. Write in the comments section, tell me in office hours, send me an email, whatever you like. Alright, see you next time.